Hi everyone, I am Chinmoy Chakraborty, Assistant Professor, Mallabhum Institute of Technology in the Department of Electrical Engineering. Today I will discuss a topic which is transient stability analysis using equal area criteria. As an electrical engineer, in the power system, we all know that it consists of lots of devices which are interconnected to each other, although the stability at every point must be common for all those devices. Here, each and every devices have their own protection from their transients. Stability of any system can easily be calculated from the generation or load side also. In our today's discussion, we will try to discuss the following topics, which is the assumptions we need to make for find the transient stability, and then the equal area criteria, the most important part of this topic, then transient stability analysis by sudden increase in the steam input, then the limiting case of transient stability with mechanical input suddenly increased, and then the concept of critical clearing time and critical clearing angle. Then we will try to follow the some cases, sudden loss of one parallel lines, short circuit at the middle of the line, and then finally the conclusion of this discussion. Now, coming to the assumptions made to find the transient stability part, first assumptions we need to make is neglect saturation, which means field current never saturates with the field flux. Second assumptions we need to make is neglect saliency, which means there is no reluctance difference between the stator and around the circumference of the rotor. Third assumption is neglect damping. As we all know, the damping reduces the oscillations. Fourth assumption is frequency is constant. And the fifth most important assumption we need to make, that is speed governor is constant or deactivated, and the final one is AVR is deactivated. Coming to the most important part of today's discussion, which is equal area criteria. Now, why this concept is required? We all know that transient stability is happen when the system goes through a large disturbance or short circuit fault. From the swing equation also, we can find the del in case of transient stability, but it is quite difficult to find the higher order derivatives in real time. So we use the modified version of swing equation or equal area criteria. From the swing equation, we know that Pm minus Pe, that is equals to Pa or m into d2 del by dt square. Now we multiply both sides with 2 into d del dt, we will get d dt into d del dt whole square, which is equals to 2 into d del dt into Pa by m. Now if we integrate both the side with the respect to dt, then we will get d dt equals to root under 2 by m into integration of Pm minus Pmax sin del into d del. Under steady state, we all know d del dt equals to 0. So we can say that integration of Pa into d del equals to 0, which represents the equal area criteria, and it shows that area under accelerating power, which is equals to area under the deaccelerating power. Transient stability analysis by sudden increase in steam input. Let a single machine system having initial shaft power Pm0 and initial electric power Pe. Now, if we suddenly increase the steam input, which means mechanical power increases, say now it will be Pm1, from the graph at point A, Pm0 equals to Pm0 equals to Pe, which means steady state condition, but from point A to B, shaft power rise up to Pm1 from Pm0. So in the path A to B, PM1 greater than PE, so there will be a difference between PM minus PE, or we can say that PA greater than 0. If we see in the other way, we know d del dt equals to omega minus omega s, but at steady state d del dt equals to 0. Here omega greater than omega s, so d del dt greater than 0, which also means rotor accelerates. Now at point B, it is clear PM1 equals to PE or PA equals to 0. So rotor not accelerates, but if we assume that the machine synchronous speed was 1000 rpm at point A, but due to increase in the steam input, that is from point PA to B, speed rise up to 1500 rpm. So omega minus omega is, there will be a difference, that is 500 rpm. So it is clear at point B, when PA equals to 0, d del dt still greater than 0, which means rotor angle still increasing. Now during BC, in this path we can see PE greater than PM1, which means PA less than 0. That means the rotor start to deaccelerates. Now in this path d del dt equals to omega minus omega s, that means there was a difference of 500 rpm. Now rotor deaccelerates means now speed start to decreasing gradually, like 1400, 1300, 1200 in this way. So still there d del dt is greater than 0 as omega greater than omega s. Now at point C, in this point PE greater than PM1, which means PA still less than 0, and the deaccelerating area A2 equals the accelerating area A1, which are shaded in the graph. And in this point d del dt omega minus omega s equals to 0, which means rotor angle will not further increase or decrease. Since the rotor is deaccelerating, the speed reduces below omega s and the rotor angle begins to reduce. The state point now traverses the PE del curve in the opposite direction with angle excursion up to del 0 and del 2 on the two sides, where the area A1 and A2 are given by A1 equals to integration of del 0 to del 1 pm minus 1 pm minus 1 minus pe into d del, and A2 equals to integration of del 1 to del 2 pe minus pm1 into d del. Limiting case of transient stability with mechanical input suddenly increased. Now the question arises, if we further increase PM1, then what will happen? From the graph, it is clear that if we further increase the steam input or mechanical input, then point B in the graph will be on the higher side, which reduces the deaccelerating area of or A2, or we can say that it can increase the accelerating area, which means A1 greater than A2. So the excess kinetic energy causes del to increase continuously and the system becoming unstable. Thus it has been clear that the system is remain stable as long as the equal area criteria is met. Similarly, we can say that the point C can also move up to a certain limit. Beyond that, at any point it will be PM1 greater than PE, which also indicates rotor continuous acceleration and the system become overdamped system or unstable system. Concept of critical clearing time and critical clearing angle. Let a single machine system having initial shaft power Pm operates with steady angle of del 0, where the electrical power is Pe, and we know that at steady state Pm equals to Pe, which is point A in the graph, Now, if a three-phase fault occurs near the bus at the outgoing radial line, then PE suddenly drops to 0 and the state point in the graph drops to point B, which means the PM will be greater than PE and there is a difference between PM minus PE. So the PA greater than 0 means the rotor try to accelerate. At this time, area A1 begins to increase and so does the rotor angle. So the point moves along BC in the graph. Now when the fault is cleared once again, system becomes healthy and transmits the electrical power PE equals to P max sin del and the state point in the graph shifts to point D from C and the rotor decelerates under the curve DE until A1 equals to A2. Critical clearing time. What is critical clearing time? The maximum time taken by the circuit breaker before isolates the circuit, that time is known as critical clearing time, which is denoted by TC, critical clearing angle. The angle which is generated corresponding to critical clearing time before opening the line circuit breaker is known as critical clearing angle, which is denoted as DC. Now from the previous graph we can write that del 1 equals to del max equals to pi minus del 0 and Pm equals to P max sin del 0. Now if we write the A1 equals to integration of del 0 to del CR Pm minus Pe into d del where Pe equals to 0. So A1 will be become Pm into del CR minus del 0 whereas A2 will be integration of del CR to del max P max sin del minus Pm into d del. So it will be become P max into cos del CR minus cos del max minus Pm into del max minus del CR. Now for stability condition we all know that A1 will be equals to A2. So if we equate both the value of A1 and A2 then we will be get cos del CR will be equals to Pm by P max into del max minus del 0 plus cos del max where del CR will be the critical clearing angle. By substituting equation 1, 2 and 3 we will get del CR equals to cos inverse pi minus 2 del 0 into sin del 0 whole minus cos del 0. Now from swing equation we know that m into d square del by dt square equals to Pm minus Pe. Now at fault condition P equals to 0, so we can write m into d square del dt square equals to Pm, and we also know that the m equals to h by pi f where m equals to h equals to inertia constant. Hence we can say d square del dt square equals to pi f by h into Pm. If we double integrate both the equation we will get del equals to del CR which is equals to critical clearing angle equals to pi f by 2h into Pm into t square plus del 0, whereas t equals to tcr equals to critical clearing time equals to root under 2h into del cr minus del 0 whole divided by pi into f into Pm. Sudden loss of one parallel lines. Let's consider that a single machine is tied to infinite bars through two parallel lines as shown in the figure. Now study the transient stability if one of the line is suddenly switched off while operating on steady load. So before switching off, the electrical power Pe1 is equals to mod E dash mod V dash divided by XD plus X1 parallel X2, where XD is the reactance near the generator and X1 and X2 will be the reactance of line 1 and 2 respectively. So PE1 will be represented as P max 1 sin del, but when the line 2 is off then the electrical power will be P2, that is equals to mod E dash mod V dash divided by x d dash plus x1 into sin del, that will be represented as P max 2 into sin del. As Initially the system operating with steady load, so PE equals to PM at point A in the graph. Immediately on switching off the line 2, the electrical operating point shifts to point B in the graph, where Pmax 1 greater than Pmax 2, as x dash d plus x1 greater than xd plus x1 parallel x2. Hence, the accelerating energy corresponding to area A1 is put into rotor, followed by deaccelerating energy for del greater than del 1. Assuming that an area A2 corresponding to deaccelerating energy can be found such that A1 equals to A2, then the system will be stable and will finally operate at point C corresponding to a new rotor angle del 1 greater than del 0. This is so because a single line offers larger reactance and rotor angle is needed to transfer the same steady power. Short circuit at the middle of a line. Let us now assume the disturbance occurs at the middle of the parallel lines, but in this case there is still some power flow during fault, so P not equals to 0. Circuit model of the system during fault is shown in the figure through one delta star and one star delta conversion. Now, before the fault, we can say that PE1 equals to mod E dash mod V dash divided by XD plus X1 parallel X2 sin del, that is equals to P max 1 sin del, but during fault PE2 equals to mod E dash mod V dash into sin del, that will be equals to P max 2 sin del, and in this time rotor accelerates and del increases as Pm greater than Pe. The system will be stable if deaccelerating area A2 can be found equal to accelerating area A1 before angle del reaches its maximum allowable value del max. By applying the equal area criteria in the graph, we can write that integration del 0 to del CR Pm minus Pmax 2 sin del into d del equals to integration of del CR to del max Pmax 3 sin del minus Pm into d del, where del max equals to pi minus sin inverse Pm by Pmax 3. Integrating the above equation, we will get Pm into del CR minus del 0 plus P max 2 into cos del CR minus cos del 0 plus Pm into del max minus del CR plus P max 3 into cos del max minus cos del CR equals to 0, or we can say cos del CR equals to P max into Pm into del max minus del 0 minus Pmax 2 into cos del 0 plus Pmax 3 into cos del max whole divided by Pmax 3 minus Pmax 2, or del CR or critical clearing angle equals to cos inverse of Pm into del max minus del 0 minus P max 2 into cos del 0 plus P max 3 into cos del max whole divided by P max 3 minus P max 2. So now we can conclude that it is to be observed that the equal area criteria helps to determine the critical clearing angle, while the critical clearing time can be obtained by numerical solution of the swing equation. At last, thank you everyone for watching and listening this topic.